Okay, this was a request to do a video for problems 6 and 7 on Chapter 2 homework. Alright, so problem 6. This says, this figure shows the velocity graph of a particle moving along the x-axis. Its initial position, it has an initial position of 2 meters at the beginning at t equals 0. So we need to keep that in mind. Alright, at t equals 3 seconds, what is the particle's position? Alright, at t equals 3 seconds, all we have to do is determine, how is position related to a velocity graph? It's the area of the velocity graph between the curve and the x-axis, or the t-axis in this case. So what's the area of this triangle? It's going to be 1/2 3 times 6. So that's going to be half of 18, which is 9. That's the displacement. If the initial position was 0, that would be the final position. But since the initial position is 2, then we have to just add that displacement to the initial position. So 9 plus 2 would be 11. Your numbers may be different than mine. For my numbers, it's 11, meters. At t equals 3 seconds, what is the particle's velocity? Well, this is a velocity graph, so all we have to do is think about, okay, what's the value or the height or the ordered pair for this function at 3 seconds? It's 0. The velocity is 0 meters per second at time equals 3. At t equals 3, what is the particle's acceleration? The acceleration is the slope of the velocity. Since this is a line, it's easy to figure out the slope. Just rise over run. So let's see, it's going to be 6 over 3. And it's negative. So that's going to be -2. -2 meters per second squared. Alright, and that is problem 6. Let's look at part number 7. To take off from the ground, an airplane must reach a sufficiently high speed. The velocity required for the takeoff velocity, depends on several factors, including the weight of the aircraft and the wind velocity. Okay, good background. Alright, part A. A plane accelerates from rest at a constant rate of 5 meters per second squared along a runway that is 1,800 meters long. Assume that the plane reaches the required takeoff velocity at the end of the runway. What is the time for takeoff needed to take off? Right, I'm going to need to get some room to work for that thing. Oh no, that's not what I wanted to do. Okay, so we have, and let's think about what we know. We know A is +5. Okay, and we're trying to find T. It says assume that the plane reaches the required takeoff velocity at the end of the runway, and the runway is 1,800 meters long, so that means the final position is 1,800 meters. That's something we know as well. So, alright, I'm going to get my kinematic equations going here, and this is kind of my way to turn the keys to start the engine. I start with A, and then I start doing antiderivatives to get the other equations. So A is 5, constant 5, so VF is the antiderivative of that, which is 5t, plus initial velocity, which we can assume to be 0. And position is the antiderivative of this velocity, so it's 5t squared over 2. I'm just going to say 2.5t squared plus the initial position, which we can assume to be 0. All right, what do we know? We know this. We can plug that in for x sub f. 1800 equals 2.5 t squared, and we got it whipped. We can just solve for t by dividing by 2.5 and taking the square root. And t will equal, approximately equal, about 26.8 seconds. So let me go back and put that in. 26.8. It says use 3 significant figures, so I did use 3 significant figures. Okay. Part B, what is the speed of the plane as it takes off? Well, that shouldn't be too hard because we've already got the velocity equation that we need. And we know the time, so that's, yeah, we got it. Vf equals 5 times 26.8. Maybe I should use a few more digits. 8, 3, 2, 8. And only round at the end. So, let's just say times 5. And that is 134.16. 134.16. Alright, and let's go back and plug that in. Three significant figures. 134.2. Because no, just 134. Three significant figures would just be 134. Alright. Part C, what is the distance traveled by the plane in the first second of its run? Alright. All we got to do is say XF equals 2.5 times 1 squared. So that's going to be just 2.5. Simple enough. .5 meters. What is the distance traveled by the plane in the last second before taking off? Okay. The last second. Well, what I might need to do, there may be more than one way to do this. That you might think of maybe a better way than what I'm thinking of right now. But since I know that it takes 26.8 seconds to take off, then the last second will be between 25.8 seconds and 26.8 seconds. So I'm going to find the position when I plug in 25.8. And I'm also going to find the position when I plug in 26.8. And the difference between those is how far it traveled during that last second between those two times. So just doing a little calculator work here, 2.5 times 25.8 squared and 2.5 times 26.8 squared. All right. 2.5 times 25.8 squared is 1664.1. And if I change it to 26.8 squared, it's 1795.6. And the difference there, let's call this, well, the change in X there is the difference which is going to be 131.5. So yeah, it went a lot farther in the last second of its takeoff than it did in the first second of its takeoff, and that's due to the fact that it's accelerating. It was going a faster velocity at the end than it was at the beginning. So 131.5 should be the answer. Three significant figures. So I'm going to say 132. I hope that's right. It may be 131. Yep, 132. Okay. What percentage of the takeoff velocity did the plane gain when it reached the midpoint of the runway? Okay, then the midpoint of the runway. Gotcha. Yeah, that's an interesting problem. All right. Okay. Let me get myself some room here. All right. The midpoint of the runway, if the runway is 1,800 meters, is 900 meters. So 900 is the final position in that case. And I can find the time that way. Just doing a little algebra. Okay. 900 divided by 2.5. And then taking the square root. I get 18.97. So plug that into VF. 5 times 18.97. And that will be 94.868. Okay, at the end of the runway, what was its velocity? Did we already answer that? I think it was 134. I thought we already answered that. I thought it was 134 point something. Let me just go back and remember if we already answered that. Yeah, we answered that in Part B. Part B, the final takeoff velocity was 134. So V takeoff was 134. So what does it ask? What percentage of the final takeoff velocity did it reach at the midpoint of the runway? So in other words, 94.868 is what percent of 134? So 94.868 divided by 134. I get 0.70797. So like, what does it want? 3 significant figures. No, let's see. It's best to the nearest percent. So that's about 71% then. 71, hopefully. That is correct. Good deal. And we've got an interesting explanation. This is a rule of thumb generally used by pilots. Since the takeoff velocity for a particular aircraft can be computed before the flight, the pilot can determine whether the plane will successfully take off before the end of the runway by verifying that the plane has gained 71% of the takeoff velocity by the time it reaches the halfway point of the runway. If it has not, the pilot knows there isn't enough time to reach the needed takeoff velocity, and he can abort the takeoff. Yeah. So that's how you do number 7. I hope this was helpful in helping you to complete and to understand those problems and Chapter 2 homework. All right, we are looking at problem number 10 on Chapter 2 homework. It says in this problem you apply kinematic equations to a jumping flea Okay. The flea jumps straight up to a maximum height of 0.49 meters. What is its initial velocity v0 as it leaves the ground? All right. Again, this is my general strategy for all kinematics problems. I start with my equations, my kinematic equations, beginning with A. A, in this case, we're talking about a projectile motion, a free fall situation, which is negative 9.8 as a constant. And so then from there, I can anti-derive the other two equations for velocity and position. So my final velocity will be the antiderivative, negative 9.8 t, plus an initial velocity. I'm going to call it VI. And that's actually what we're going to be looking for. They call it V0, but I'm calling it VI, but it's the same thing. Or V sub 0. Alright, my position equation, I'm going to call it Y since it's vertical. Final position equals the antiderivative of the velocity. So it's negative 9.8 t squared over 2, which becomes negative 4.9 t squared plus VI sub VI t. Remember, we're anti-deriving these things with respect to t. T is the variable. The other things are constants. T is the only variable. Okay? So V sub I is not a variable. It is a constant. It does not change. Whatever the initial velocity is, that's what it is. These things are changing with time. The final velocity depends on what time it is. That tells you what your velocity is at that time. The final position is telling you the position at a certain time t. All right, so the antiderivative of this constant is that constant times t, plus the initial position, which I'm going to say is the ground, which is 0. So we don't need that term. All right, now I'm sitting here thinking, what do we know in these equations? All right, I'm looking for V sub I. I don't know the time. I don't know t, but I do know V sub f. All right, see if you know what V sub f is. It doesn't give it to you in these words, but it is the situation that dictates here that V sub f has to be a certain thing. It says he reaches a maximum height of 0.49. That means his final velocity at that maximum height is 0. Because that's what it is. When you reach your maximum height, for a split second there, your velocity is 0, and then you come down. So I'm going to say 0 equals negative 9.8 t plus V sub I. Again, I'm looking for this, but I still don't know t. So maybe I can go somewhere else to find that t. Do I know YF? Do I know the final height? And the answer is yes, I do. It is 0.49. So let me try that. 0.49 equals negative 4.9 t squared plus V sub I t. Okay. All right, from here, I've got two equations and two unknowns. Here are my two equations, and my two unknowns are V sub I and t. That means, algebraically, if I'm good at algebra, it's all over but the crying, right? It's all over but the work, the algebra work. So let's see what we could do there. We could say V sub I equals 9.8 t here. Just by moving the negative 9.8 t over to the other side, we get 9.8 t equals Vi, and then we could substitute that in for V sub I there. So that gives me 0.49 equals negative 4.9 t squared plus 9.8 t times t, which is going to be 0.49 equals negative 0.49 t squared plus 9.8 t squared. Got my decimal point in the wrong spot there. The 0.49 and the 4.9 are a little confusing. Get your numbers mixed up. Alright, so then these are like terms. That becomes 0.49 equals 4.9 t squared, because negative 4.9 t squared plus 9.8 t squared is positive 4.9 t squared. Now divide by 4.9. That gives me 0.1 equals t squared. Square root both sides. And t will equal, what's the square root of 0.1? Square root of 0.1 is 0.316. 0.316 is the time. Alright, that's the time that it takes to get up to that maximum height. I haven't answered the question yet. The question is, what is the initial velocity? Well, now I can take that time I just found and plug it in right there for t to get VI. So V sub I equals 9.8 times 0.316. Which is 3.099. Okay, so let's go plug that in and see if that is right. Three significant figures. 3.099 would actually round up, wouldn't it? So it's 3.10. That's good stuff. Alright, let me show you another way you could work that problem also. Besides our three kinematic equations for A, V, for acceleration, velocity, and position, there is one more kinematic equation that's, for me, a little more hard, a little more difficult to remember, because it's not just an antiderivative thing working. It's actually, it comes from already putting together the VF and the Y F. But it is very handy sometimes. Like this problem, it's very handy. And it is VF squared equals VI squared minus 2A delta S. Okay, where delta S is the change in position. In this case, we'd even have, we wouldn't say delta S, we'd say delta Y. But S is just a generic letter for whatever direction, X, Y, Z, whatever. You just, S is the generic position letter. So this one is helpful a lot of times when you don't know time, but you know the other stuff. So that's the case here. So let's just see how this would work in this problem. Final velocity, we've already said, at the maximum height would be 0. VI is what we're looking for. We know A is 9.8. And we know delta S. Delta S is the change in position during that movement. So it's the change in, it goes from 0 to 0.49, so it'll be 0.49 minus 0. So it's just 0.49. Delta S, the change in position, is 0.49. And look, I only have one variable. I don't have to do substitution or anything. It's just a straight up algebra problem from here. We end up getting 2 times 9.8 times 0.49 equals V squared, VI squared. So square root both sides to get the answer. And we get VI equals the same thing we did before, 3.099 or 3.10 to three significant figures. Yeah, that's a little bit easier way to do it. Part B asks us for the time. And actually, the first way we worked it already gave us a lot of information about the time. I'm trying to remember what that answer was. Well, I don't really remember what the answer was, but regardless of that, I can go back to the equations I had. And I could do a couple of different things. I could get the time from this part. And here's a couple of ways you can do that. We know the initial velocity was 3.1. And we could say the final velocity, we have a couple of choices there. We could say that the final velocity, okay, is 0. So when you leave the ground, you go up, you come back down. If you find the time it takes to go up this way, then it's because of the symmetry of the situation, it's going to be the same amount of time going this way. And so if you find the time it takes to go up to the top, just double it, and that'll be the time it takes for the entire flight. That only works if you jump from the same height you land. So if you like jumped off a table, that would not be the case. If you jumped off a table and hit the ground, that would not be the case. If you jumped off a table and landed on the same table, that would be fine. But the other option, so we could say 0 equals negative 9.8t plus 3.1. And we could solve for t that way and double it. Alright, another option is whatever your initial velocity was going up, when you go all the way up and come all the way back down, your final velocity will be the exact opposite of your initial velocity. So if your initial velocity was 10, your final velocity when you hit the ground is going to be negative 10. So we could put negative 10 in for that. Not negative 10, sorry. I was using my example instead of what was in this problem here. Sorry, negative 3.1 and positive 3.1 here. And I could solve for t that way, and I don't have to double it there. Whatever I get for that t, that is the answer here. Alright. One more way you could do it is to do this equation. The YF, the final position when I hit the ground, the final position is 0. And you could solve for t in this equation. And that t wouldn't have to be doubled either. Whatever that t is the answer here. So whichever way you want to do that, at that point you have multiple paths to get that. Let's see what the answer is. This answer is for t. If I use this one, I just subtract 3.1, divide by negative 9.8. So 3.1 divided by 9.8 is 0.316. Then I double that, and I get 0.633. 0.633. Let's try that. That is correct. Alright. Alright. We're doing problem 13 now. A hotel elevator ascends 200 meters with a maximum speed of 5 meters per second. Its acceleration and deceleration both have a magnitude of 1 meter per second squared. Alright. I could go ahead and write a lot of things about my kinematic equations for this problem. Here the acceleration is 1. That is an ugly equal sign. My goodness. It's kind of hard to write on this computer screen. my final velocity is the antiderivative of that, which is 1t plus the initial velocity, but the initial velocity is 0. So I'm just going to leave that term off. The final position is the antiderivative of the velocity with respect to t, so that's going to be 1t squared over 2, or 1/2, or 0.5 t squared, plus the initial position, which I think I'm just going to say that that's 0 also, to make it simple. I don't have any reason not to, so I don't need that term. And then I could also go ahead and write my other kinematic equation that's the one that I always have trouble remembering. That's VF squared equals VI squared plus 2A delta S. So in this case it would be, well, let's just determine which one we should use. The way to determine which one to use is just figure out what you know and start plugging it into places, and then if you end up with a variable in the equation that you can solve for that you want, that's what you use. And if it doesn't work the way you attack it the first time, just go back and try a different one. Alright. So in this case it's moving up to full speed, so that full speed is 5 meters per second. From rest, that would be 0 meters per second. So that's my VF and my VI. So that looks like this would be a good one to use. Put 5 here. Put 0 here. Do I know A? Yes, I know A. That's 1. And my only missing thing is delta S, which is exactly what I'm looking for. I'm looking for how far it moves. And that is what the delta S is. That's the change in position, or the displacement. There's another way we could do it too. I'll show you in a second, but let's just go ahead and get the answer this way. 20. So if I plug 5 into there, it becomes 25 equals 0 plus 2 times 1 times delta S. So 25 equals 2 delta S. Divided by 2, delta S equals 12.5. The other way we could do it is we could have used this one. We could say the final velocity is 5. And we could solve for t there. We would just get t equals 5. That's not what we're looking for, but maybe that'll help us. We could take that 5 for t and plug it in there to get YF. So YF equals 0.5 times 25, which is also 12.5. So that's also gives me the answer in a different way, that the final height that you would get to in that scenario would be 12.5 as you accelerate from rest up to 5 meters per second if you had an acceleration of 1 meter per second squared. So let me go over here and plug that answer in, 12.5 meters. Correct. How long does it take to make the complete trip from bottom to top? Alright, let me go back to where I was working. And we also had that. So the time we're looking for the time to make the complete trip. Well, the complete trip is 200 meters. All right, I'm thinking this problem is going to be, it's going to take some steps here. It's going to take some thinking, some real thinking, because I think what we got is we got 3 situations. The elevator accelerates but then it goes the same speed for a while. And then it gets to the top. When it's going to stop, it's got to decelerate. So we got a positive A. And then in this situation, we have a constant velocity. A equals 0. Constant velocity. And then in this situation, we got a negative A. It's going to be -1. All right. So I got to figure out how long it takes to do each one of those phases. All right, so let's try it. Let's try the first phase. The first phase is, I think we already figured that out when we worked the other part A. The first phase, that final velocity, it reaches that maximum velocity of 5. And so the time for that first phase is 5 seconds. And then phase 2 will be, it will have no acceleration. It will just be, let me redo my kinematic equations. A would be 0. VF would be VI. YF would just be VIT. And that whole VI is just 5. 5 meters per second the whole time. All right. What did we answer in part A? 12.5, right? The answer to this was 12.5 meters. That's going to help me, because phase 3, we also know that that's going to be the exact same thing as phase 1. If it took it 5 seconds to accelerate from rest to 5 meters per second, if the acceleration is 1 meter per second squared, then if the acceleration is -1 meter per second squared, and I'm changing my velocity from +5 and back down to 0, it's going to take the same amount of time. That's also going to be 5 seconds. This took 12.5 meters to happen. This is also going to take 12.5 meters to happen, which means phase 2 is going to be 200 meters minus these two. So it's actually going to be 175 meters. 200 meters, but you got 12.5 meters at the beginning, 12.5 meters at the end. Take those away. So you're taking away 25 meters. So phase 2 was 175 meters. So now I can just say 175 for this YF equals, the VI is 5, and I'm just looking for T. So divide by 5, I can get T equals 175 divided by 5 would be, is that 35? I think it is. 175 divided by 10 is 17.5, but if I divide it by 5, that's going to be twice what that is, so twice 17.5 is 35, right? Let me just check myself. 175 divided by 5 is 35, yep, so 35 seconds there. Now, I think we're ready to answer it. The total time for this trip, all 3 phases, accelerating, then going to constant velocity, then decelerating, that whole time is going to be 35 plus 5 plus another 5. So that's going to be 45. That was a pretty challenging problem. Let's make sure we're right before we count our chickens. You entered does not recognize it. Maybe I should just put S. Yep. Good deal. We got it right. All right, number 14. David is driving a steady 26 meters per second when he passes Tina, who is sitting in her car at rest. Tina begins to accelerate at a steady 2.7 meters per second squared at the instant when David passes. How far does Tina drive before passing David? I remember doing a problem like this in the lecture, I believe, but let's do this. So let's do David's equations and Tina's equations. David's acceleration is 0. His final velocity equals his initial velocity, which is just 26 the whole time. So I'm not going to use y, I'm going to use x because this is a horizontal situation. His final position is just going to be the antiderivative of 26, which is just going to be 26t. All right, Tina's equations. Her acceleration is 2.7. Her final velocity is the antiderivative of that, which is 2.7t, plus the initial velocity, which is just 0 for her because she starts at rest. And her final position is the antiderivative of that velocity, which is going to be 2.7t squared over 2. What's half of 2.7? 1.35. 1.35 t squared plus her initial position, which we might just say is 0. Now, when Tina passes David, right at the moment she catches up with him and passes him, these two equations are equal. These two values for xf, their positions, are equal at that moment. So I can just set them equal. 26t equals 1.35 t squared. And I can solve for t. If I move that term over, and then factor out a t, set this equal to 0 and this equal to 0, .35 t equals 26 divide t equals 26 divided by 1.35, 19.26. 19.26 seconds. All right, that doesn't tell me the answer I want. I want how far. But now it's easy to find that answer because I just plugged the 19.26 in for t in Tina's position equation. I can figure out how far she went. So her xf will be 1.35 times 19.26 squared. Okay, 1.35 times 19.26 squared. That's a pretty good bit. That's 500.78 meters. That seems high, but maybe it's right. Let me put it in and make sure. 0.78 meters. All right. What is her speed as she passes him? That should be easy also, because I've got this equation right here I can plug the time into to get her final speed at that moment. So her VF at the moment she passes him is 2.7 times that time, 19.26. And so that's going to be 52.002. which is, I think I'm just going to put in 52. Well, it's got three significant figures. So 52.0 meters per second. That is correct. All right, I hope going over these problems will help you not only to do well on the homework, but to understand better how to attack these kinematics physics problems. Again, my strategy is just to get my equations. I can start with A, and I can get V and position from there. And there's also that other one that comes in handy sometimes too. And then just start plugging stuff in that's given to me and find what I need from there. See you next time.